Hello dear students, welcome you all. In this lecture, I am going to extend my discussion on the Fermi theory of beta-decay. You know very well that in the previous lecture, I have derived an expression for the probability of the emission of an electron that has momentum in the range PE to dPe, right? So that expression was G square, right? MIF whole square divided by 2 pi cube C cube H cut power 7 into E naught minus E electron whole square PE square dPe. And this is equation number 1. So this was the expression that I have derived in the previous lecture, and this expression tells us about the probability of the emission of electron that has momentum in the range of PE to dPe, or we can say in the range of P to P plus dP. Right. Now this expression has been derived, by ignoring the Coulomb correction, or we can say Coulomb interaction. You know very well, when electron, if we take the case of electron, in case of electron emission, when it is coming out of the atomic nucleus, it is definitely, interacting with the electrostatic field of the atomic nucleus, because the electrostatic field of the atomic nucleus is attractive, it is positive, so it is attracting the electron. Whereas if we are considering the emission of a positron from the atomic nucleus, then in that case the positron will experience a repulsive force, right, we can say, due to the positive charge on the atomic nucleus. So these two type of interactions, these has been ignored here, and we have derived this expression by not taking into account these interaction. So we can say that we are considering the wave function of the electron that is emitted from the atomic nucleus as the wave function of the electron that is moving freely. But in reality, the wave function of the electron or positron would be modified by some factor, and that factor will depend upon the Coulomb interaction between the atomic nucleus and emitted electron or positron. As far as the lighter nuclei for which Z is less than 10, in those lighter nuclei, we know the positive field of the atomic nucleus, electrostatic field, it is very weak, so we can ignore. But when Z is greater than 10, right, in that case it is mandatory, it is important to take into consideration that interaction. Right. So here in this lecture, I am going to discuss the importance of this Coulomb correction term. So it has been found that if we want to take into account this interaction, Coulomb interaction, then we have to modify the wave function of the electron that earlier we were taking as the wave function of a free electron. But we should replace this wave function of the free electron by this, wave function that is modified by a potential, or we can say by interaction. So the factor that determined that how much interaction was there, that factor depend upon the wave function of the electron in the Coulomb potential and the wave function of the electron in the free space. So we define that factor, right? That is given as a F Z E electron. It is given as the ratio of the wave function of the electron in Coulomb potential. We can say wave function of electron in Coulomb potential whole square divided by the wave function of electron in free space, or when the electron is fully free. So this factor is known as the Coulomb correction factor, right? So we should multiply this factor in this expression if we want to calculate the exact value of this transition probability. what I want to say, I'm saying that this wave function of the electron that earlier we have taken simply as this psi electron, it will be modified by the wave function of the electron multiplied by this factor, right? So when we take into this into consideration and we calculated this factor, right, it is found that this factor is equal to f z e electron is equal to 2 pi eta upon 1 minus e power minus 2 pi eta. This is the value of this factor, as it has been calculated by using different quantum mechanical results, right? Here in this expression, this one, eta is equal to ze square upon 4 pi epsilon naught h cut nu, right? For electrons, and it is equal to minus z square upon 4 pi epsilon naught h cut nu, right? This is for positrons, this factor eta, right? So this is the factor that we are taking here, right? Now if I put this factor here, then this factor will change this expression, this one, right? We can multiply this factor here, so we will get the probability of electron that has momentum in this range, that is equal to g square mif whole square divided by 2 pi cube c cube h cut power 7 multiplication by the factor f z e electron into e naught minus e whole square pe square dpe. So this is the expression that I got, this one, after putting this value of this factor here, right? So this is the modified expression for a transition probability, right? So this Coulomb interaction, as I told you, Coulomb correction term is very, very important when we are taking into consideration the nuclei that for which Z is greater than 10, and we can say that in those nuclei the Coulomb field is strong and it is interacting, it is accelerating the positrons and it is deaccelerating the electron, because it is attracting the electron and it is repelling the positron, right? I am drawing a graph that will show you, the meaning of this mathematics. This one. So this is the graph that is used for understanding the behavior of the beta particle spectrum. This is dn upon de naught, the number of observed final quantum mechanical states per unit energy interval, right? And this is the kinetic energy axis, kinetic energy of the emitted electrons or positrons. So when we studied this relation and we plotted it here in this way, then it is found that these are the graphs that I am showing you here. This is the first graph, right? This is the graph that we obtain when no Coulomb field is there. Coulomb field is ignored, right? But if we take Coulomb field into consideration, then the graph becomes this one for you can say this one in this way, right? It is for beta negative or electrons, and it becomes this is for beta positive, right? Or we can say it is for a positron and it is for electrons. So this is the behavior of this relation that we observe here. Now you can see that after reaching at this point, that these two graphs, they combine with each other, right? And we are getting the similar kind of behavior. But when the kinetic energy is low, this is the low kinetic energy region, right? That we are seeing here. In low kinetic energy region, we are getting three different graphs. This is the graph when no Coulomb field is taken into consideration, and these two are the graphs that we observe for either beta positive decay or beta negative decay. So we can say that when the kinetic energy is very low, then in that low kinetic energy range, we are observing more electron, right? This is the meaning of it. Electron graph, number of observed electron states per unit energy range are higher as compared to the number of positrons, right? Energy states, they are on this side, right? And electron on this side. So what is the meaning of it? The meaning is when the energy of the emitted particle is low, the Coulomb field is playing a very, very important role. It is attracting electrons, so we are getting more electron states in the low energy range. But when the energy is high, kinetic energy of the electrons is high, they can easily overcome the Coulomb potential, and then after at this point we are getting similar kind of behavior for both positron and electrons. But positrons, you can see here, now for the positrons, the graph is on this side, or we can say the number of observed states are low. Why? Because the positron is repelled by the positive field of the atomic nucleus, right? So we are observing fewer particle, these positron particle in the low energy states, and more electron particles in the low energy states, right? So this is the meaning of this entire mathematics or equations and a Coulomb correction. That is very, very important in the low energy range. As you can see, once again I am saying that when the kinetic energy reached at this level, then after there is no distinction between the two graphs and we get only one graph. These two graphs coincide with the graph that we observed with the no Coulomb field, right? But with no Coulomb field, we are getting this one, Coulomb field, this one, and at this point the two graphs coincide, right? You can also understand this graph in this way, that the in the low energy range, right, positron spectrum has fewer slow positron. Slow positron means those positrons which have low kinetic energy, right? They will be observed very low, right? Why? Because they will be pushed by the Coulomb field. But if we look at the low energy range, then we have more electrons. More electrons, why? Because they are attracted by the Coulomb field, right? And they are behaving differently than these positrons, right? This is the way in which you can also see the analysis of this graph, right? So thank you very much. This is all about it.